So what we're going to do is basically just go over some examples for the most part. But before that, we're going to take a review on what the heck work energy is, right? So what you guys should have done last week is, let me sit down. What you guys should have done last week is that we have this theorem, and that's the work energy theorem. And that basically tells us that the kinetic energy in our state one, if we have two states, a body going through two states, and by two states, I mean the velocity is changing, for the most part, right? If a body is going through two states, the kinetic energy plus any work done on that body due to any external forces is equal to the kinetic energy in state two, right? So we'll write that down. So the kinetic energy in state one is equal, or plus the work done from state one to two, is equal to any kinetic energy in state two, right? So that's always true. And we'll see how, like, even though it might not first off make sense, like, okay, how is that possible? We'll go through examples and you'll perfectly see that this is always the case, right? There's some things that if it happens in real life, you might not like know because, oh, there's other external forces that you don't see, but this is the rule of thumb, right? Okay, and if you have any questions, I run through stuff pretty quick, so you have to stop me, right? You have to stop me, right? If you don't understand something, you have to speak up. Understood? Fun stuff, okay? Okay, for kinetic energy, before what we had is simply 1/2 mv squared, right? 1/2 our mass multiplied by our velocity squared, and that's when we're dealing with particles, right? That we don't take into account how like big they are. Like if we had a box before, it might look like a box, but inherently, or for the fact, we're representing it as a very small particle, right? An infinitesimally small particle, right? So before that, in simple mode, we had translation, right? Translation. And how we represent that in terms of a formula, the kinetic energy of translation for a particle is 1/2 mv squared. 1/2 multiplied by the mass multiplied by the velocity of that particle squared, right? And that's our first case. Now that we're dealing with rigid bodies, right? Now we have the ability to rotate, right? Not only translate. So we have the second case. We introduce a second case, and this is a more specific case, where we have pure rotation, right? The first example is pure translation, and the second example is pure rotation, right? About an axis. And if we have pure rotation, we're going to try our best to simulate this pure rotation about a point that does not move. Or we have to do this, right? And that inherently is the instantaneous center, right? So instead of 1/2 mv squared, now we're going to have the rotational version of this, right? Before, where mass represents the resistance to motion, basically, we're going to introduce the mass moment, or introduce resistance to basically motion or translation. We're going to introduce now the mass moment of inertia, which is a resistance to not translation, but a resistance to rotation, right? So 1/2, let's write this one, 1/2 I, the mass moment of inertia multiplied by IC, which is resistance to rotation multiplied by, what's the angular version of linear velocity? Well, angular velocity, right? Beautiful stuff, huh? Okay, so we have omega, right? Omega squared. Okay, some cases are not as simple as this, right? For the most part, things aren't just purely translating or purely rotating. They're doing both, right? So in that case, we have this lovely third case, which we're going to try our hardest not to use, but sometimes we have to use it, right? And that is both of these, we're accounting for both the translation kinetic energy or translational kinetic energy within our body, as well as the rotational kinetic energy within our body, right? So 1/2 mv about the point G, right? Remember, mg squared plus 1/2 the mass moment of inertia about our point G, omega squared, right? Okay, understood up to now. We're good. Okay, that covers kinetic energy. That is what T1 or T2 can be. Those are the only two possible options. How about work? Well, work can fall into two separate categories. If we draw this like so, work can fall into two separate categories. Work is caused by any external forces or external moments acting on our body. External forces or external moments, right? So let's write that. Forces or moments. Right? So those are our two basic scenarios, if you will, right? The work due to an external force is equal to the integral of F the force, multiplied by an infinitesimal piece of length, aka the path, right? So once we take all of those little lengths that force acts on, it gives us a path, right? So F dr, right? Obviously, we're not dealing with, for example, our length isn't like a function or whatnot, or it's a constant function, but it's not like changing. We're not doing any fun stuff yet, you know? We're still the simple stuff. So from this, what we have is, what this simplifies to once you do the derivations and whatnot, which we're not going to do, is a dot product, and then once you keep going, the dot product is a scalar value, and that's very important. Notice that this entire formula is a scalar. You don't have any vectors. So what that means is you can't conceptually, or you have to conceptually understand what positive work is and what negative work is. And that's the hardest part of any of these problems. You have to determine whether it's positive work or negative work. And that's what we're going to hopefully clear up. But this formula does it. This formula is one of the ways that will help you determine whether your force or whether your work is positive or negative. So we'll do that. So it's FD cosine of theta, right? Or cosine is, so it's your force multiplied by the path your force follows, multiplied by the cosine between those two vectors, right? If you have your position vector and your force vector, the angle between them will determine whether you do positive work or negative work, right? Okay, in terms of moments, it's a bit simpler in that you have any work due to an external moment is equal to your moment multiplied by a differential theta element, right? And then once we add all those theta elements together, we get a full path. Again, we're not going to really use this integral way, but we're going to use the simpler version, right? Because we deal with mainly constant things, constant thetas, right? Okay, so in that, the work due to an external moment is m multiplied by theta, right? The moment multiplied by the path the moment runs through. How do we determine it's positive or negative? We'll do a few scenarios to see if that helps a bit. Okay, we'll cover translation first. Just some scenarios to understand, okay, how do we use this? How do we determine whether work is positive or negative? Because that is the most important thing. You don't have any vectors to tell you, okay, this is in the positive direction. I define my coordinate like this, blah, 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 right? There's a conceptual way to do it, and there's a way with analytical formula, but the conceptual way is easier, in my opinion, at least. But we'll go through both. Yes?
Brother, I just have a quick question. The first scenario, you mean FR cosine?
FR,
Because it was DR?
That's good, yes, that is true. This is the typical way we represent it. F, like that, and if you go in your textbook, it'll say FDR, but for if I were to do F dot R, people would think, or some people would think it's a radius, but it's not a radius, right? And I can't really do DD, right? Because you're going to get confused, and you guys look clueless right now. So I don't know. So we're gonna take into account. We're gonna keep it with R. But that's a good point. This R in this case is the same, right? It's a differential element on our path, dr, and then D represents the full path, right? Okay. We can go to scenarios. Let's say we have a good brother, and he is free falling, right? This is the ground, perhaps, and then our good brother free falls, right? He free falls a distance of 50 meters, just for example, right? Random values. I don't care about the numbers, right? Actually, we're big kids now, right? We can use vectors, right? So let's make this a position vector, right? This is 50. R is equal to 50 meters. Right, for the most part. It's in the negative j direction, right? Okay, what forces act on my guy right here? What's the main force? If any of you guys say drag, I'm going to get mad. What's the main force that pops up? The weight, beautiful, Fg, right? What way is it acting? Down. You sure? You have to be confident. Yes, of course it's acting down. Okay, Fg, right? And then this guy also has Fg, right? Let's say hypothetically, no drag, blah, blah, blah. These are the only forces acting on our body. Why, my question to you now is why is this guy, or this guy down here, why is he faster? If he starts from rest up here, his velocity is 0. Why is he faster near the ground?
Gain some potential energy because
Beautiful. Yes. Even though this force may be the exact same thing. Let's say he weighs 1 kilogram and the gravitational constant is 9.81. the force in newtons is 9.81 newtons, right? Going down, and it's still the same down here, right? So why does he get faster? Well, he said it. You have an energy transfer, right? Gravity is transferring, or this potential energy is being transferred to kinetic energy. And therefore, what you have is, if the first thing we said today was that this formula is always true. Screw gravitational potential energy for now. We'll get to that in conservation of energy. But if this formula is also true, is always true, here, my initial velocity is 0, making my initial kinetic energy 0, right? So I only have work is equal to kinetic energy in my state 2, near the ground. I know this guy has a large velocity now. So it's impossible for my kinetic energy in state 2 to be 0. To be 0. So therefore, I have kinetic energy in state 2. Therefore, T2 cannot equal 0. Right? So I have to have another term here to represent why was this energy can be created. Why is he faster? Well, that's because we have work. The question is whether it's positive or negative work. Does gravity in this case do positive or negative work? What do you think? I'm not Professor Gian. I will pick on people.
It's a negative work.
It's negative work. Why do you say that? And are you sure? What's your idea?
I mean, we always assume it as negative or negative work.
Why do we do that?
Because we always assume upwards is a positive direction versus down, which is a negative direction.
Work is a scalar value, though. There's no vectors associated with work. And if you're claiming that we have negative work, for example, let's say our potential energy in state 2, T2 is equal to 1/2, in this case, mv squared, right? Let's say our mass is 1 kilogram, 1 kg. Let's say our velocity, I don't know, is 5 meters a second, right? In this case, if I do this, T2 is going to equal 1/2 multiplied by 5 squared, which is 12.5, if I'm correct. 12.5 joules. If I have negative work, I'll get to you in a second. If I have negative work, this means that a negative work, or it should be U, negative work is equal to a positive value, which is impossible, right? A positive number cannot be equal to a negative number. So, no, it's not negative work, actually, right? Why is it not negative? Well, I'll go.
Is it positive because when you take the dot product of the gravity, the force and the displacement both downward?
Beautiful. Yes, exactly. Amazing, amazing stuff. So it's inherently, it is positive. Why do we do this? He said a good point, which we'll get to. You look at the equation and it doesn't make sense. Why did I say we draw this as a vector? So we do not get confused with stuff like this, right? So, okay, let's say I want to do it with the equation method that this sir right here just said. I'm going to say that F, what was our equation for work? We said F d cosine of theta. My F in this case is Fg. My R in this case is this vector right here, right? And it's pointing down. And then cosine of theta is going to determine whether this work is positive or negative, right? So I'm going to write it down. So this is my position vector. This is my work. What is the angle between these two vectors? 0, right? And what is cosine of 0? Don't get it wrong, please. 1, yeah, beautiful, right? Where cosine starts up here and then it dips down, right? It starts at 0, it starts at 1, right? So therefore, if cosine of 0 is 1, then we have positive work, right? How do you determine this conceptually? Well, conceptually, I look at my force, and that's one way to determine, okay, you have positive work in this case. How do you determine this conceptually? Well, conceptually, I will look at it, I will say, is this force increasing my velocity or decreasing my velocity in this specific scenario? I'm asking you guys, is it increasing my velocity or decreasing my velocity? Increasing your velocity, right? So therefore, I'm adding energy to my system, right? I'm adding work, right, due to external forces. And therefore, my work has to be, my net work in this case, has to be positive, right? So yeah, that is how we determine that. Let's say, for example, let's say we had drag. Drag is acting in the opposite direction. F, drag. F, drag. We use those two same scenarios for that matter, right? What's the angle between my position vector and my drag force? Pardon? 180, yeah. What is cosine of 180? -1, and therefore my work is negative, right? And then I look at it in a conceptual manner, I see that my drag force is trying to decrease my velocity, right? Do you see that it's trying to decrease the velocity? It's trying to slow you down, right? Okay, beautiful stuff. So that's a conceptual idea of how to do things. We're going to go over two more quick examples. One with a box, right? We have this box, right? And let's say our good brother is adding a force to this box like this, right? Force applied. And then we have a force in the opposite direction, force of friction. And what other two forces do we have? What other two forces do we have? Gravity and normal force. Beautiful stuff. So we have the normal force and we have gravity. Amazing, amazing stuff. Okay. My question to you now is, if my thing starts from rest, right? My box starts from rest, and now all of a sudden in this state it's moving at a specific velocity. I want you to tell me what forces cause work and whether that force is positive or negative. Let's start with one. Does this a force applied cause positive or negative work in this scenario? Positive work. Why? I heard three things and they were all quiet, and I have bad hearing, so what?
The angle between the force and the direction of the motion
Is 0, right? And cosine of 0 is 1, and that makes us positive. And if I also want to think about it another way, it's increasing my angular velocity, or it's increasing my linear velocity, and therefore it's adding work to my system, positive work, right? How about friction? Negative, right? Beautiful. How about my normal force? 0. Why?
Because the angle between the direction and the both normal and just normal.
Yeah.
It's 90.
It's 90 degrees, right? Cosine of 90 degrees is 0, right? Making this entire equation go to garbage, right? And that's the exact same thing with my gravitational force in this case, right? So in the previous example, people, like at least I was taught that gravity doesn't do work for the most part. That's incorrect, right? Gravity does not do work in this case, but sometimes there are cases where gravity will do work. Sometimes there are cases where gravity do positive work, negative work, right? So it all depends conceptually, and this is the only part that's difficult, right? Or a bit challenging is that you have to determine whether it's positive or negative. But as soon as you get these two concepts, you're good, right? Last example, or last scenario, I guess. This is an example. This is baby stuff, you know. Okay. We have this lovely bar, right? It starts from rest. Actually, that's a bit. We're not going to do that. We're going to do it the other way around because this is easier. We have this slender rod, right? It's rotating about this point right here, right? Let's say it starts from rest, and then all of a sudden, due to an external moment, it's now rotating at an angular velocity, right? Let's say it's over here now. Is this moment causing, and obviously it goes through a theta value, right? Is this moment causing positive or negative work? Or is it even doing work at all? Yeah, you can just talk out loud. Positive work. Yes, why?
Because, like, on the other side of the equation for T2, there's positive rotational energy.
Exactly, yeah. Perfect. Do what he did. Look at the equation and see, does it make sense for one side to go up and then one side, for example, this side would start at 0, right? So it goes to garbage. And this side will be positive, right? Because you have positive rotational or a positive angular velocity, right? Basically this guy. Therefore, my work has to be positive. And another way to do it, and if you just want to look at it conceptually, which is what comes from the formula, is that, okay, does it increase my angular velocity or does it decrease my angular velocity, right? And in this case, it will increase. Yes, sir.
Isn't it counterclockwise? Was it clockwise in this case and negative?
That's a good point. But again, we have to understand the work is a scalar value. It doesn't have to do with any vectors, right? It's a scalar value. For our final equation, what we're going to have work is equal to just a number, right? It's just a value. It doesn't have any vector or position associated with it, right? So the best way to look at it is either through the formula or this conceptual. Just remember, if it's increasing my velocity, positive work. If it's decreasing my velocity, negative work. Okay, we're prepared now to go into some examples, right? Or two main examples, which we'll go through today. Okay, times 8, 4, oh, it's over here. Okay, so the wheel shown in the figure below weighs 40 pounds and has a radius of gyration of 0.6 feet about its mass center G. If it is subjected to a clockwise couple moment of 15 pound-foot or 15 pound-feet and rolls from rest without slipping, determine its angular velocity after its center G moves 0.5 feet. The spring has a stiffness K of 10 pound per feet and is initially unstretched when the couple moment is applied. Take the difference between A and the IC as a constant value, right? So immediately, we're going to go, we're going to have an organized methodology, a framework to solve our problems, right? So immediately, so I don't start rushing back and forth through my question, I'm going to put down my givens. I won't put down all of them, but I'll put down most of them. What am I given in this question? And let me rephrase, that is a question to you lovely people. Yeah? Radius of gyration, right? Radius of gyration. And that is equal to 0.6 feet. What am I going to use that for?
Instead of,
What and what?
instead of moment of inertia, you use kg.
Beautiful, yes. What are you going to say?
Same thing.
Same thing. Yeah, I'm going to use it to find my mass moments of inertia. No, so I'm going to use it to find my mass moment of inertia, right? Eventually. And we can even do that now, but it doesn't really matter. So that's, I'm going to run through it because you guys are a bit slow, so we don't have enough time. So my FG force or my weight, in terms of FG or my weight, I'm not going to write W because you guys might confuse it with work, even though we don't use W as the symbol for work anymore. But let's say FG is equal to 40 pounds, right? My weight. And we're going to say, or we know that this moment that's applied is 15 pound-feet. My initial velocity of my body G is 0 meters per second, right? I know that I have a no-slip condition down here, which allows me to use my instantaneous center, which allows me to make this point right here my instantaneous center, right? And then what else do I have? Well, we have that this spring has a constant, right? We have this spring right here, has a stiffness of 10 pound per feet, right? 10 pounds per feet. There are also some other small things in here. For example, my radius, right, of this cylinder or whatever, or disc or whatnot, is 0.8 feet, right? And those are my givens. What does this question want me to find? What? Distance? No, that's one of my givens. Yeah, that's a good thing, right? My my position, my displacement of point G, right, from initial, or in this case, initial, to my second point is going to be 0.5 feet. It's a good thing. I missed. Thank you. What is I looking for? Pardon? Angular velocity of energy. Do you agree? Beautiful stuff, right? So that's my unknown. That is what I'm trying to look for. Unknowns. Unknowns, my angular velocity of my center G, or I just say angular velocity at state 2, right? Immediately, I don't care that I was given a schematic in this diagram. I'm going to quickly draw something, right? Just for my own understanding of the question, right? And these entire steps, you should do as soon as you read the question. Don't start figuring out what to do and blah, blah. Immediately, you should be doing this, right? To be efficient, save time, and have this like framework to follow, right? Okay. So what did we say? Schematic, right? Schematic. Beautiful stuff. We're going to draw before and after, but we're going to focus on after. We're basically drawing this lovely thing once again. So let's say what force, let's actually put down the points. So this is G, right? This is my ground. This is my IC, right? And this is my point A. What forces are acting? Actually, let's put this radius here as well, 0.8 feet. What forces and moments are acting on my body? Spring force at A. What direction? Right or left? Right or left? Yeah, right or left. Yes, just say it next time. Left? Beautiful stuff. Left, right? Okay. Your left is also my left. That's good. So left. So force of the spring, right? Beautiful stuff, right? Because trying to, as I rotate this stupid thing forward, right? The spring is initially unstretched, which is also a very important point, right? As I try and rotate this thing forward, my spring is going to try and bring it back, right? So that is what we have to write down. So you're right, it's to the left. What other forces do I have? Yeah. The moment, right? Is it clockwise or counterclockwise? What do we say? What? Clockwise, right? So about center G, we'll just put the moment. The moment. What other forces do I have? There's a bunch of ones. Gravity and normal, right? So I have my Fg, my weight, and my normal force. I believe there is one more force. And we could write it, we could not write it. This is just me being picky.
Is that the friction?
That's the friction, right? But it's not kinetic friction. We have a no-slip condition, right? So it's just the friction that acts like, for lack of a better term, like as a reaction. But we'll explain, and it does no work, which we'll get to in a second. But I think that's all the forces we have. Speak up now, because again, I can be wrong, so sometimes I forget things, right? So I think that's all the forces, though. So we're good. I'm going to quickly draw this guy over here, just to indicate, just in the back of my mind, just to see the kind of picture that's happening, right? My like how my thing is moving, right? So this is my initial condition, right? It starts at a velocity, if this is my point G, right? My velocity over here is 0 about my point G, right? It starts from rest, and then this distance that it travels, let's choose this color, this distance that it travels right here is 0.5 feet, right? And then what I want to do now is add my kinetic reactions, if you will. What direction is my velocity in this state? And again, this is my state 1, and this is my state 2, right? What reactions do I have? Like, okay, reaction is a bad word. Maybe velocity. Like, what way is my velocity about point G, and what way is my angular velocity going in state 2? It's not a trick question. Pretty intuitive. Velocity is going this way, right? To your right, right? And that makes sense, right? The question literally tells us that. So my velocity about point G is going this way. So Fg is equal to, or let's not, we don't know what it's equal to right now, but it's equal to this way. About my angular velocity, clockwise or counterclockwise? Clockwise. I need a confidence clockwise. This isn't a trick question. Clockwise, right? Beautiful stuff. Bravo. Right? Okay, beautiful. So now I have everything, right? This is a classic work energy theorem problem. So the first thing I'm going to do specifically in this problem is I'm going to put down my work energy theorem. So I'm going to write number 4, work energy theorem. Theorem. Right? Beautiful stuff. Make that shorter. Good stuff. Okay. I'm going to write down my formula and expand from there. Right? I'm going to write down my formula and then branch off with what I know, what I don't know, and whatnot. Right? Any questions so far? Right? Okay. Good stuff. And you guys have to ask if you guys don't know what's going on. Any question, you guys have to ask, right? Because unless you guys want to figure it out on your own, on an exam and learn new things, right? Okay. The work done from state 1 to 2 is equal to my kinetic energy at state 2. Okay. My kinetic energy at state 1, what is it? 0. Why? Pardon? It's at rest, right? My angular velocity, if I go up here to my formulas that we did before, my angular velocity is 0, which makes this term go away. My linear velocity is 0, which makes this term go away, right? Good stuff. So I can say at rest, I could say it's 0 or whatever, gone, because velocity is equal to 0, or just say, let's say because rest. Because rest, right? This is not the case for my kinetic energy at state 2, but we'll get to that in just a second. How about the work done? Well, I have a bunch of forces and moments here, right? So any one of them, I'm going to analyze, I'm going to go through each one of them to see which one may cause work and which one may not cause work, right? So in this case, and let me know if I forget anything, I can have work due to the spring. Let's say due to the spring, work due to the spring. I can have work due to the normal force. I can have work due to the force of friction. I can have work due to Fg. And I can have work due to my moment. Right? Is that everything? Is that everything? Yes, right? Good stuff. Let's analyze and let's go, remember, we're going to do our framework where we're going to branch slowly off each item. So let's do that with our kinetic friction at state 2. And in this case, this is one of those scenarios where I have pure rotation, right? Pure rotation about which point? Not about point G, because point G is also moving, right? Point G also has a velocity. The question said we have a no-slip condition at the IC, right? Where the disc will contact the ground, right? So there, I can basically represent my body's rotation as purely rotating about the IC throughout these instantaneous moments, right? Is that understood? Yes or no? Yes.
Just a quick question.
Yes.
Is that because we don't have any friction on that point, or is it because?
Yes, it's because nothing is sliding, right? That's a good question. If I were to have kinetic friction here, that means my wheel is slipping, if you will, right? But since I don't, what's happening in, we'll go through it fine. What's happening basically is that at every single instant, right, as this wheel is rotating, at every single instant, the velocity of my IC, my instantaneous center, is 0, right? At every single instant. Okay, how does that make sense? Well, after a differentially small, an infinitely small distance, right? This IC is constantly changing, right? Now it's rotating a very, very small piece of theta about this point. And then after a differential, let's say dr, it's rotating another very, very small d theta, right? A very, very small piece. And then at this point, it's purely rotating about another so it's incrementally moving, right? You're looking at, okay, this is the IC now. Let's move it just a little bit, and now let's see the rotation. Let's move it just a little bit, see the rotation. And you're going to do that for the entire theta that your wheel is rotating, right? Right? Okay. And in that, if, for example, if you're going to, let's say, we'll get to it, actually. I'm skipping ahead. But we're going to get to why the angle is also the same, right? The angle of rotation about your IC is the same angle of rotation about your point G, right? We'll get to that in just a second. But long story short, we're going to have the kinetic energy in state 2. Since we know it's pure rotation, it's going to be 1/2 multiplied by my moment of inertia about my instantaneous center multiplied by my velocity squared, or my angular velocity at state 2 squared, right? Good stuff. We are going to start with this guy, right? Or actually, let's eliminate ones. Or actually, no. Let's do one by one. What does the work do to this moment? What does the work do to a moment that we discussed before? What is the formula? Moment times theta, right? Beautiful. We can start with that, or we can start with m d theta, right? And then, because we have easy stuff, we're gonna go to m theta, right? Do I know what my moment is? Look at givens. Do I know my moment? I do or I do not? I do, right? Beautiful stuff. So I have my moment. I know that it's 15. It's 15, right? Or 10? 15, right? 15 pound-foot. Or pound-feet or whatever. What is my angle, theta? What does my angle theta represent in this example? It represents how much this moment acts through, right? It represents how much distance, if you will, or how much in terms of an angular distance, and that's theta, it's an angle. How much has my moment applied through, right? So if my wheel rotated 30 degrees, right, and my moment acted through 30 degrees, this is my angle, right? Oh, that's 45, it looks like. But regardless, right? So I'm looking for that angle it rotates from state 1 to state 2. How can I find that? Well, easy stuff with my displacement formulas, right? My displacement formulas. So, I can find my angle of rotation in this scenario about my point G, right? I can say that using the formulas that we know from kinematics, that my displacement, and this comes from Vg is equal to is it R cross omega or omega cross R? Because that matters. Not in this case, but it matters generally.
It's not R times theta equals A.
R times theta is equal to A. R times theta is equal to A. Yeah, we're going to get there. You just used a bit of different letters, so my brain got confused. But we'll get there, right? R times theta, right? My question is R before theta or is theta before R? I don't remember. I'll look at the answers. Wait up. Where is it?
You're talking about the circle, right? Like with the angle of the circle, the arc, and the radius?
Yeah,
Isn't it
'cause
omega R?
That's my
Omega
question.
dot-
Yeah, you
omega
guys
dot
failed.
dr.
I asked you a simple question.
It's omega dot dr, I guess.
Omega
If
dot-
that's your question.
1 second. Yes, it's R before omega, or it's R before theta, right? It's R cross theta. Keep it like that, right? So in this case, it's R cross omega. This is the general formula that you know, right? It relates the angular velocity with linear velocity, for that matter. If we integrate this, we get what this guy said over here, right? If we integrate this, we get SG, or in this case, he called it A, right? It doesn't really matter. The displacement of point G is equal to my radius, for that matter, multiplied by what?
Angular acceleration.
Not angular acceleration. I'm integrating. I'm going backwards in time. I'm going backward. If I derive this formula, then I'm going to acceleration. If I integrate,
Oh, you're going back. My bad.
no, not angular velocity,
Delta T.
theta, right? Right? My displacement, right, is equal to my radius multiplied by theta, right? What do I want to find? Well, I want to find my theta, right? So I just rearrange this formula. Theta is equal to my displacement of point G divided by my radius, right? And what radius is this that we're talking about? What radius is this that we are talking about?
The wheel.
Pardon?
The wheel.
The wheel, yes, correct. Right? And if we're being honest, we should, yeah, it is the wheel. So if we evaluate this, what do we end up getting? What is my displacement of point G? How far has my wheel moved? I'm purposely not having the diagram up here because it's simple. Let's zoom out. 0.5 feet, right? My displacement of my point G is 0.5 feet. It's moved 0.5 feet, and my radius is simply 0.8, right? So 0.5 feet divided by 0.8 feet. What will that give me? I have my calculator somewhere here. Because I can't trust you guys adding the numbers or doing something like that. What is it? It's what? It's 0 point? Oh, I did 0.5 times 0.8, and then I got confused. 0.625, what are the units? Radians, right? Or degrees?
Radius.
Radians, right? This formula is always in radians. 0.625 radians. Right. Okay. Do I have everything I need to evaluate this equation right here? Yes or no? Confident yes or no? Yes, right? Okay. Come down here. I'm going to say that my work, due to my moment, due to my external moment, is equal to 15 pound-feet multiplied by 0.625 radians, right? And what is that going to equal? Well, let's do that real quick. It's going to equal to 9.375 joules, right? Or not joules. We want to stick to our units, so feet. All right, let's just keep it like that. It's a unit of energy, but it doesn't really matter. Okay, is it positive or negative? Is this work done positive or negative? Positive. Why? Pardon?
Making
Making
it spin.
a spin. That's not a valid answer. We are increasing the velocity, right? If you take away all these forces, right? Screw everything that's happening here. And we just had the moment, right? Is it trying to make my wheel go faster or slower? Trying to increase the velocity, the angular velocity, or decrease the angular velocity? Decrease the angular... What? Is it trying to increase the angular velocity or decrease the angular velocity? This moment right here. Trying to make it spin faster, right? It's trying to make it spin faster, it's trying to slow it down in the direction that it's going right now. You guys aren't confident. I might be tricking you guys. Tell me, I need a confident answer. Faster, right? Right? It's trying to increase the velocity that the body's already in, right? It's not a trick question. So that's what we're going to do, right? So this is positive. Positive work done by the moment force. Okay. How about the work done by the spring? We're going to write this down. All right. We know that work due to a spring is equal to what? 1/2 kx what? Squared, right? What does x represent in this scenario? Right? Yeah, how much the spring is from its initial position, from its unstretched length, how much it is stretched, right? That represents inherently how much energy you have, right? That's what represents this x value. Okay, we're gonna keep going. Do we have everything in this formula yet? We can find everything, but do we have it at this point in time? No. Okay. Why? We do have it?
Yeah.
Do we have x?
Yeah.
Are you sure?
Yes.
And when I say are you sure, I mean you're wrong.
Yeah.
Okay, fine. What is x?
It's the displacement.
That's a very, very good point. It's wrong, but it's it's a good question. We cannot assume that, let's say I have a very, very stiff spring, right? Not necessarily, if I stretch a spring with a low stiffness, right? It'll spring out very much, right? Even if I move 0.5 feet, it might stretch the exact same amount. But if I have a very stiff spring, right, it might not stretch the same amount I move, right? And the other way around, if I have a very, 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 very strong spring, like those ones in engines and whatnot, that is designed to not spring that much. So even if you pull it, right, from its initial length might be this much. Whereas I'm moving, if you look at the computer, if I'm moving this much from here to here, let's say my spring was already this amount, right? So it's not stretching my displacement, right? So it's different. If I want to be very specific, well, I have to look at where my spring is attached. And where my spring is attached is this point right here at A, right? Okay. I can say that, okay, I don't know about point G, whether my spring has stretched this amount or not, but about point A, that will properly, because the spring is attached here, right? That will properly determine how much my spring has stretched. That will accurately determine. So my displacement of point A, I can replace in for x. That is a value for, sometimes it might be the same, right, as what you guys just said, right? And that's the intuitive answer. Sometimes it isn't. And that one case that it isn't, we need to check for. That's where mistakes come from. Okay, and this is A, and this is A prime. What is my displacement of point A equal to? Using kinematics, which we kind of just did, but kind of not as well. What do you think? Give you a hint. We have our IC, right? We have a point that isn't moving. What I want to do whenever I'm finding displacement, or whenever I'm finding velocity, or whenever I'm finding any of these, or not acceleration, accelerations gets too fun, but for velocity and displacement specifically, I want to find places where, okay, I have a point that's fixed, right? And then I want to relate where I want to find my displacement, or where I want to find my velocity about a point that is fixed. In this case, what is my fixed point? My IC, right? So I want to relate my position of my of this top of the sphere, right, with my IC, right? So I'm going to relate it with my IC. So therefore, I can do that, right? So my position or my displacement of this this point A to find my my stretched spring length is equal to, like we said before, R. And what R would this be in this case? It would be from my IC, or it would be 2A with respect to my IC, right? A with respect to my IC multiplied by the theta of rotation, right? The amount that my thing rotates. So theta at state 2, right? How much I have rotated. And this brings us back to our initial point, which we made before, and then I said I'll mention it after. Do I have theta of rotation? Yeah, I do. But one thing to note is I calculated this theta. This represents, for example, my theta about, for example, if it started over here, let's say, for example, or we have this value, so we can say that it's 6.25 radians, for example, hypothetically, right? And then this is my new point A, and then we drew it differently. Like it rotated this amount. But that's about point G. Why can I say that this theta about point G is the same one about my IC? It doesn't intuitively make sense, does it? Or does it? I don't know. Let me know.
Is it because the radius is different?
Pardon?
Is it the radius between point A and point G and point
It is different, but yeah, that's the scenario. Like why can we say that this theta of rotation, we're going to use the same thing, right? Why can we use the exact same thing we used about point G? Well, that brings us back to the idea, yeah.
Is it like a similar triangle?
Not exactly. It's a good idea, but like not exactly. It brings us back to that same thing that when we're taking our rotation about the IC, we're looking at very, very, very small elements, right? And let's make this 30 degrees for simplicity, right? Let's say that intuitively, I say that, okay, from state 1 to 2, my cylinder or sphere or disc, whatever, has rotated 30 degrees, right? That's intuitive to think about, right? Easy stuff. In this case, it's still rotating 30 degrees, right? But we're looking at it a different way, right? In this case, I'm looking at, because my IC is always changing, right? So at this point, okay, let's say this is my state 1. In my state 2, I'm taking a very, very small distance, an infinitely small distance away, right? In my next moment, my DR, this is my IC now, right? And in this distance, I've rotated maybe, I don't know, 0.001 degrees, right? I've rotated a very, very infinitely small amount. And then I look at my next point, infinitely small amount, infinite. And I add all those together, it may not seem intuitive that, okay, how can the rotation about this point be the same as the rotation about this point, right? And the answer to that is we're just looking at smaller intervals, right? We're just looking at very, very small intervals. But anyway, Gauss concept, if you know it, you know it. If not, then just use the formula at the end of the day, right? We have determined through that we can replace x with the displacement of our point A, right? So 1/2 KSA, right? Displacement of our point A. What did we say our displacement of point A is equal to? Is equal to R cross the theta that we travel, right? So the work due to the spring is equal to 1/2 K R from A or 2A with respect to the IC multiplied by, and we could square this and square this guy, multiplied by the theta that we travel through at state 2, right? Do we have everything to solve our problem now? And any questions, most importantly, you have to ask. Okay, then at least answer my first question. Do we have everything to move forward? Do we have all these values set in stone? Do we have them? Yes? Beautiful stuff. What is K? My stiffness, right? What is the value? 10. 10 pound per foot, or pound per feet. What is my distance from A to my IC? A wonderful hint, it is your radius times 2. So if you can do that math, you know, maybe you can give me an answer. Our good brother here is answering the questions, and here is answering the questions. So I need you guys to, what? 0 point? Almost. Move a decimal place. Yeah. 1.6 feet, right? Right? From here to here is just the radius times 2. Right? The radius here and the radius here. Right? So 0.8 plus 0.8. Beautiful stuff. What's the theta? As we confused you even more with. Well, you better get this right now. What is the theta? Yes. 0.625 radians, right? 0.625 radians. Beautiful stuff. We can go ahead with calculating this now. We have all the values. I'll put it in a calculator. Let me know if you guys get the same results. It's 10 times 0.625 squared. What do you guys get? What did you wonderful people get? Yes, sir. Yes.
Can you explain the RAIC?
Yeah? RAIC?
Yeah.
Okay, no problem. We're looking at the displacement of this point, right? From here to here, right? This is my displacement of A, right? I can represent this tangentially, right? With the formula that we used before and whatnot, right? In kinematics. And that formula is that this displacement in the same way. For example, if I was going to represent, easier to think about, people to understand displacement for some reason. Velocity, that's why I said velocity down here. The velocity at this point right here is equal to this radius multiplied by this omega, right? That's the case with everything, right? Now we're going to integrate, right? Therefore, this position, if you will, that vector's kind of wrong, but regardless, this position, SA, is equal to this radius multiplied by this theta, right? So it's the exact same concept, just transferred over to displacement, right? Does that kind of answer your question? Yeah? Okay, good. You guys had an extra 20 seconds to find that stupid value, so I'm expecting a number. 50? Almost. What? You guys, there's still a chance to drop the course, I think, before drop data. I'm just joking. What is the value? 3.125. Okay, let's do this manually then. 1/2 times 10 is equal to 5, right? That gets rid of this part. Multiplied by 1.6 squared. What's 1.6 squared? And 0.625 squared. 1.6 squared is 2.56. Multiplied by, it's too late now, you must, 0.625. I'm already disappointed, so it doesn't really matter. Right? Times 5 times 2.56. It is equal to our lovely whole number 5, right? So our work due to the spring is equal to 5. Let's just keep it pound feet. Is it positive or negative work? I need this quickly because we have an entire other question to go through.
Negative.
Quickly, please. Why?
Opposite direction of the motion.
Yes, that's a very good point. Yes, it's opposite direction of the motion. So if I use my cosine, right, the angle between my position vector of point A, right, if this is my position vector, or if this is A prime with respect to A, as my vector, my force is in the opposite direction, and therefore cosine of 180 is -1, making my work negative. You can also think about it, okay, just conceptually, it's not acting at point G, so it's kind of difficult, but you can simulate this. This is basically a moment, right? There's a moment about point G, and therefore it's acting, if I were to represent it as a moment, it would be in the negative direction, right? It would be opposing my motion. It would be trying to slow down. And even conceptually, if I have this spring, if it's already moving this way, right, it's trying to bring it back, this spring, right? This force of the spring is trying to pull back on it. Good stuff. We have the easy ones left. So, does the normal force do any work? Why? 90 degrees, right? If I look at the displacement, right, of my IC in this case, IC prime with respect to IC, it's perpendicular, so 90 degrees, right? And what's cosine of pi over 2? 90? 0, right? And the exact same thing with FG, right? You get the jazz. So we're going to cross them out. We're going to say because perpendicular. So bang, bang. Because perpendicular. I said perpendicular because. So because perpendicular. So it's easy as that, right? For the most part. Oh yeah, that's not the right one. This guy. because perpendicular. How about the force of friction? Does it cause any work? Does it do any work? Intuitively, you might say yes, but because we have a no-slip condition, it's no, right? Work has to deal with velocity, right? It has to increase or decrease my velocity. If I were to remove all of these forces, all of them, my friction force in this case is for lack of a better term, it's like a reaction, right? It's not kinetic friction, right? If I were to remove all these forces, this friction force would not cause a moment and rotate it in the other way, right? It's just there to simply like support my motion, right? Any questions about that? I won't go into depth because it's not really applicable and we're running low on time, but long story short, if it says no slip condition, and the simplest way to think about it is at this point, do you have any velocity? Right? From here to here, do you have any velocity? Or like, I should say this in a different way. You know how like, since we're changing our IC, right? Our IC is changing after every instant, right? So this isn't a force that acts from IC to IC, right? From this point to this point. It isn't a force that acts. That would be kinetic friction, right? It would be trying it would try to slow down our rotation, right? Instead, it's a force that acts like momentarily, right? At each moment, we have this force just supporting our rolling motion, right? Well, yeah, good stuff. Any questions? Right? Okay. So we can cross this guy out as well. So, no work. Okay, so what we determine is that the moment causes work and the force of the spring causes work. Now we have to determine, we have everything on this side of the equation. What we want to find, we go back to our unknown, we want to find our angular velocity, right? So to do that, what we're going to do is, do we have our moments of inertia about the IC? Like, or at least can we find it easily?
Yes.
Right? Okay, beautiful. I'm looking back at this, I'm looking at bird's eye view. I know that in this formula, I have one unknown and I can solve for it. That's a good start, right? Okay, we're going to quickly find our mass moments of inertia about the IC. The parallel axis theorem tells us that the mass moment of inertia about our IC is equal to our moment of inertia about our point G, right, about our center of mass, plus the mass of our object, right, of our body, multiplied by the distance from the point where you're trying to find the moment of inertia to the mass moment of inertia at point G, right? And in this case, it's just our radius. Do we understand that? Yes or no? Yes. Okay. Good stuff. So this is squared. What is my mass moment of inertia about point G? We were given the radius of gyration. What is it?
mk squared.
mk squared. mk squared. I need someone else to confirm that because I don't really remember. I think it's mk squared. It's not 1/2 mk squared, right?
It's MK squared.
It's mk squared. Thank you. So mk squared plus mr squared. I keep going. MIC is equal to m. What's k in this case? 0.4, right? Yes, no, maybe, perhaps. Yes. 0.4 squared plus the radius squared is 0.8 squared.
It's
0. Who said yeah, bro? I'm just joking. It's okay. So 0.6 squared. Okay, it's 0.6, yes. And the mass in this case, what is my mass? What is my mass? 40 pounds. That is beautiful stuff. Absolutely incredible. Amazing. It's not 40 pounds, right? It's not a pound mass. It's a pound force. This represents our weight. That would be like I'm giving you newtons, right? I'm saying that you weigh 40 newtons, right? We're not going to put like the mass there. That's not our mass, right? We have to divide by, if Fg is equal to mg, right? To find our mass, we have to divide by g. And in the foot-pound seconds unit or system of units, that is 40 pounds, right? So our force divided by our gravitational constant, which is 32.2 feet per second squared, I think. I'm not sure. Yeah? Okay. Beautiful stuff. We evaluate this. What do we get? What do we get if we evaluate this? 40 divided by 32.2 multiplied by 0.6 squared plus 0.8 squared. What did you guys get? 1.24. Yes, I got the same thing. So 1.24 2, what are the units of mass moment of inertia? The units of mass moment of inertia. What are they in SI units?
Slug times feet squared, right?
Amazing, yeah. You're almost there. You're getting there. But eventually what we're going to do, slug is the equivalent of kilograms in the foot-pound-second unit, or foot-pound-seconds system of units, right? So it's slug feet squared, right? Or perfect foot squared, yeah. Beautiful stuff. Do we have everything to solve this problem from this equation up here? I'm going to make everything much, much smaller. Do we have everything to solve this problem? Do we have everything to solve? I see some nodding. I need to hear a firm yes. You need to be confident, right? Okay, good stuff. We isolate our stuff. We bring it down to our variables, right? Um plus us, and we forgot to say that this is negative, right? We know it, but we forgot to write it down, is equal to 1/2 multiplied by my moment of inertia, but my IC, omega 2 squared. I simplify this formula. I get my omega is equal to 2 times my work, right, divided by my IC, my moment of inertia by my IC, and that's the square root of that, right? Square root. If I do that calculation, what do I get? I need you guys to confirm as well. And remember that some of the stuff is negative, right? We determined whether it's negative or positive before. 375 minus 5. Let's just check it in case we did something wrong. Yep. So what did you guys get? Yes, sir.
2.65.
Beautiful stuff. That's the correct answer. 2.65 radians per second. Beautiful stuff. And that's how you do this problem, right? We went through it a lot slower than you should, right? But now that you know the framework, that's how you follow, right? You start with givens, unknowns, and then schematic, and then you actually start with your equation and then break off from there. We're going to quickly do the next problem, right? And that is this lovely guy. Okay. The 10 kilogram rod shown in the figure below is constrained so that its ends move along the grooved slots. The rod is initially at rest when theta is equal to 0 degrees. If the slider block at B is acted upon by a horizontal force of 50 newtons, determine the angular velocity of the rod at the instant theta is equal to 45 degrees. Neglect friction and the mass of the blocks A and B. Okay, we're going to write down givens real quick. Again, we're not going to write down everything because we're going to try and deter. You should write down everything, right? Because we're trying to teach here, right? So we're going to try and figure stuff out as we go. Some general information. We know that the mass about point G of our rod is equal to 10 kilograms, right? Theta is equal to 0 at state 1. At state 2, theta is equal to 45 degrees, right? Friction and mass of the blocks can be neglected for now, right? And then our force P is equal to 50 newtons. And then I think, for now, that's all we're really going to write, right? And we'll determine stuff as we go. For unknowns, what does this question want us to find? What does this lovely question want us to find?
Mass of blocks A and B.
No, not exactly.
Angular velocity.
Angular velocity, right? Of our blocks or rod? Are you sure?
Of the rod.
Amazing. Yes, exactly. We want to find the angular velocity at state 2 of our... Pardon? It's okay. It's okay. No problem. So we want to find the angular velocity at state 2 of our rod. We're going to quickly draw a schematic, right? I don't care that it's drawn right there. Just so I personally understand the question and what's going on, it gives me a chance to think about, right, like a break, right? I don't want to be rushing, oh, let me put down this formula, let me do that, because that's how people get lost, right? And another very important tip, at least in my opinion, is to have these formulas, for the most part, memorized, right? Because it just that you lose your train of thought when, okay, I know how to do this, let me go look at the formula, I come back, oh, where was I again, right? So you want to have these on the tip of your tongue, right? Okay, so let's draw this very quickly. So we have this lovely guy right here, and we're going to draw it at state 2. State of block is like so, and then this guy is like that. For the most part, we have our ground here. And obviously, I'm not going to draw the constraints and all that garbage, right? This is our point A. This is our point B. From here to here is 0.4 feet, or 0.4 meters, and here from here is 0.4 meters. This is my point G, right? That's my point B. What forces do I have? Quickly, please. The applied force, right? At my block B. Perfect, thank you. P is equal to 50 newtons. Beautiful stuff. What other forces do I have?
Gravity and normal force.
Gravity and normal force. How many normal force? Yeah. Where does my gravitational force act?
Go down. Oh,
Yeah, where at? What point?
center.
At the center, right? At point G. I don't have a gravitational force at points A and B. Why? Because we're neglecting mass, right? Gravitational force is equal to mass times the gravitational constant. If your mass is neglected, your force is 0 there, right? But for the bar, we have a force, right? So this is Fg. What other forces do I have? You said a normal force. Where do those normal forces act? It's easier to look at it on this diagram while I draw something else. So I'll give you a second to think about that. Let's see. It starts up at here, maybe.
Would there also be a force acting on that way?
Exactly, yeah. Perfect. That's our normal force that we're talking about, right? Like that. Maybe it starts off like that. Who said normal force at point A? Normal force at point A, that's what he said. What other normal force do we have? Normal force at point B, right? So normal force at B and the normal force at A, right? Okay, beautiful stuff. I think we're good for now. Let's draw our kinetics, right? Or yes, sir.
What about a force acting on point A up and down? Would there be a force?
That's a good point. At this point, we don't care about the mass, right? So we're not really gonna, like, to have a gravitational force here, you understand, right? So yeah, because it's massless, we don't care about these forces that happen here, the reaction forces. Okay, where were we? We're gonna draw the kinetics. What is the velocity of, let's start with point B. What's the velocity of point B? Is it purely in this direction? Is it going this way? Is it going this way? Whatever your mind imagines. What is it doing? Just conceptually. And it's easier to look at it over here. Is it going right or left? Let's say that, if you guys don't want to be creative. Left, right? Okay. Velocity of point B. And then we'll just say this for you. The velocity at A is coming like this. Right? The velocity at G in this specific instance, since it's 45 degrees, it will be like this, Vg. And we can determine that via kinematics and whatnot. But we're going to jump to IC method like later on. Or there is two ways to find Vg in this scenario, right? You can use the long kinematic like analysis, right? We can relate Vb to Va, right? We can say Vb is equal to Va plus R B with respect to A times the angular velocity of this rod, right? And then we can find Vb, or we can find, from this you will get that Va is equal to something with omega, right? And then what you're going to do is you're going to relate Vg. You say Vg is equal to Va plus blah, blah, blah. And then you're going to find, long story short, via kinematic analysis, fun, whatever, you're going to find that Vg is equal to something omega, right? And that's what we're going to do. A much, much easier way to do this is, since you know your Vb and Va act in this direction, you're certain, right? You can find your instantaneous center. In this specific scenario, at 45 degrees, you have an instantaneous center. And how I do that, how I do it specifically, is I draw a line perpendicular to my velocities, right? And then if I do that, I will find that these lines intersect, and I know that is my instantaneous center in this example, right? I want to find Vg, right? To do that, about my IC, I know that VG is equal to since my instantaneous center is not moving, it would be IC, my velocity of IC, plus R with respect to G with respect to my IC, about omega, right? My IC, the whole point of using an instantaneous center is that this isn't moving, right? So this goes to 0, right? So I'm just left with this lovely tangential formula, which we know and love, right? How do I have this value right here? This is what I'm trying to find, so that's good, right? This is what I'm trying to find. Do I have this lovely guy right here? This distance, and if you want to figure it, do I have this distance right here? Well, not now, but I can find it, right? Let's make everything disappear for a second. VG, we determined that my IC is over here. I want to find this distance. What are ways I can find it? What's a way I can find it? I know that this angle right here is 45 degrees. What ways can I find it? Well, let's break it down into smallest. Oh, go.
So we can use the Z and get 45 degree.
Exactly. Yes. That's from the bottom you're talking, right?
Yeah.
Yeah.
You can use the cos or sin. Sorry, you can use the cos 45. Since we know the one part, you can get the other part.
Exactly.
And you can use the a squared plus b squared equals to c squared.
There are so many ways to do this. Like, yes.
I would just say use tan.
Amazing. That's also an option which we'll do. But what he said is perfectly correct, right? You can have fun with it. You can do whatever you want. But in this case, to simplify things, and because we're running out of wonderful time, we're going to say that VG, right? We want to find this distance right here from our IC. We want to find this vector right here. Well, we're going to say that since this is 45, and we know that this angle right here, okay, sorry. So this is right here, and then this is right here. My IC is over here. I want to find VG, and that is this distance right here. Right? I know that this angle right here is 45. I know that this angle right here is a 90-degree angle, so therefore this is also 45. Right? I know this distance, right, because it's given in the problem, 0.4 meters. Therefore, tangent is equal to what? Opposite over adjacent, SOHCAHTOA. So tangent, I said fangent. Damn. Tangent of theta is equal to opposite over adjacent. In this case, I'm trying to find my opposite. So tangent of 45 degrees is equal to what I want to find, right? RIC or R to G with respect to my IC divided by 0.4 meters. What is that? What's tangent of 45? Quickly. No, calculator. You should know this. No. I'm just joking, by the way. I'm sorry. It's no, not exactly. It's not 1/2. 1, right? You know, sine and cosine of 45, it's square root 2 over 2, and then it's the same thing, right? At 45, it's the exact same thing for sine and cosine. So tangent is just sine over cosine. So the same thing over the same thing is 1, right? So tangent of 45 is 1. So you have 1 multiplied by 0.4 is equal to your lovely RIC, RIC with respect to G, or the other way around, I'm sorry. But regardless, you get your value to be 0.4 feet. From that little geometry fun, we get that this is equal to 0.4 meters. I say feet, I'm sorry, but it's meters, right? I just sped through that because we have to actually do the question. I don't want to waste time on it after. Okay, now that we determined that, we're just going to put it up here. R2G with respect to my IC is equal to, what did we say, 0.4 meters, right? We just determined that. Okay, good stuff. From this now, we're going to go into our kinematic, or not kinematic analysis, but our work energy theorem. So for work energy theorem. And we might go like 9:55, I'm sorry. Theorem. Leave if you have to. Okay, good stuff. So we start with our work energy theorem, right? So the kinetic energy in my state 1 plus any work that happens from state 1 to 2 is equal to my kinetic energy at state 2. Is that correct? Yes or no? Yes, no, maybe. I don't know. Yes, right? Confident yes, right? Beautiful. Do I have any energy, or do I have any kinetic energy at state 1? Yes or no? No, right? It's at rest. Beautiful stuff. At rest. What forces, what external forces or moments can cause my work? everything, right? We're going to look over everything very quickly, right? So it could be my FG force, right? I could have work due to my FG. I could have work due to NA. I could have work due to NB. I could have work due to my force P, due to my external force P, right? We're going to look through all those scenarios. In this case, this is an example of where I have translational rotation or translational motion as well as rotational motion at this state too. So therefore, I can't have that beautiful formula that we used last example, right? I have to use the full-on formula which describes my motion for kinetic energy, and that is simply 1/2 mv about my point G squared, and that's why we found Vg, right? Plus 1/2 my mass moment of inertia about my point G multiplied by my angular velocity at state 2, which we are trying to find, right? Any questions at this point? It's very important that you understand. Yes, no, perhaps? We're good, okay? Okay, good stuff. Basically, what we're going to do now is we want to find our angular velocity. That's what the question wants us to do, right? So before that, we need to figure out these lovely guys. I'm going to tell you straight off the bat, and we're going to cover them first. Does the normal force do any work to my system? No. Why? Exactly. If I look at my normal force in this case, let's look at NB first. NB, what is the position that my force travels in? What is the position vector, right? It starts over here, and then it comes over here, right? So this is R, B with respect to O, if we call this point O, right? And then my normal force is NB. Therefore, if I use my dot product, or my work formula, F, D, cosine of theta, the angle in this case is pi over 2, or 90 degrees. So therefore, my work done is 0, right? So this goes to garbage, and the exact same thing here, right? They're perpendicular to each other, so therefore, my work acting is 0. So both of these, 0, we cross them out because they're both perpendicular, right? Good stuff. With regard to let's start with this P force first, right? For this P force, does it do any work? Well, yeah, it does. How can I determine this distance, right? It's the exact same distance that this displacement that it covered, right? So this is the one that I'm trying to find. How can I find this right here? How can I find this distance down here? Using a bunch of trig functions, right? I know that this is 45 degrees. I know that this is 0.8 degrees, or 0.8 meters. Therefore, this distance right here is equal to what exactly? Cosine of theta is equal to adjacent over hypotenuse. And I'm trying to find adjacent. Therefore, it is equal to 0.8 multiplied by 45 degree, multiplied by cosine of 45 degrees. What is cosine of 45 degrees? Root 2 over 2. Beautiful, right? So 0.8, root 2 over 2. And this simplifies to 0.4 multiplied by root 2. Everything good up to now? We're good, right? Beautiful stuff. So that's my displacement, right? What is the angle between my displacement and my vector of force? 0, right? So is it positive or negative work? Positive work, right? Beautiful stuff. So for this guy, we're going to say FD cosine of theta. We figured out that my D is 50 newtons, right? Multiplied by, we just said, 0.4, if I remember correctly, multiplied by square root 2, multiplied by, this is in meters, right? Meters, multiplied by cosine of theta. And theta in this case is 0, so this is 1. So this is my work due to my force, P. Right? Last but not least, my FG force. And this is going to take a few minutes to explain, because this is the most important part of the question, right? Okay, I apologize. Basically, I know that my force, my work done due to FG, if FG will do any work, is equal to a force multiplied by a distance, multiplied by cosine of the theta, the angle, the cosine of theta, which is the angle between my displacement vector as well as my force, right? Okay. We're going to go up to this diagram because it explains it better. Let's say, for example, initially, my system looked like this, right? When it was straight. Let's zoom out a bit. Maybe it looked like this in the beginning. Initially. Would you agree to say my point G is about here? Would you agree to say that? Or let's make it even more specific. Since it's 45 degrees, we can even say that it's perfectly aligned like this. Let's say, for example, right? Does that make sense? Yes or no? Yep. Okay. So we can say that FG acts down here, right? Do you still agree? FG acts here and FG now acts here. Right? Yes or no? Yes. Right? Okay. Stay with me. What is the displacement vector from my initial position in state 1 to my second position in state 2? Would you agree that it is this vector right here, R? Would you agree? Does it make sense? Right? Okay. Now I'm going to split this into components, which I'm allowed to do, right? I'm allowed to split it into an R component, to an X component, and to a Y component, right? Do you still agree with me? Right? Now I'm going to look at them separately. I'm going to analyze them separately. I'm going to see the work done by gravity in the X direction, and then I'm going to see it in the Y direction, right? In the X direction, for this specific scenario, with these vectors, does gravity do any work? No, right? Why? 90 degrees. How about in the Y direction? Yes, right? So that is the path I'm going to use, right? I could do them separately, but one of them is going to become 0, so I might as well ignore it, right? And this beautifully translates into the next topic, which we'll do on Thursday, and that is, what is gravitational potential energy? Well, it's simply mgh, right? Does that not make sense? That's perfectly what we see here, right? It perfectly aligns, right? So the path that this gravitational force follows is purely in the Y direction, right? And that's what we're going to do, right? And last but not least, is it positive or negative work? Positive work, right? Because my direction vector is going down and my gravitational force is going down. And that's the only part. So I know that in this case, my gravity force is mg, right? Multiplied by my path. In this case, since I know I'm going to run through it, this is 45 degrees, right? And I want to find this path right here, right? I know this is also 45. So what is this distance right here? What is this distance right here? It's 0, what? What is it? Use your cosine and sine. We're already late, hurry up. Come on.
0.4 times cosine of.
Beautiful, times cosine of 45. So 0.4 times cosine of 45, which is square root 2 over 2, which becomes 0.2 times square root 2, right? Do you agree, yes or no? Yes, beautiful. I'm just going to write it, 0.2 times that. Cosine is positive as we discussed, right? They're in the same direction, angle is 0. Whatnot. Beautiful stuff. We do this, your work due to gravity is equal to mass. What is our mass? 10 times 9.81, so 98.1 newtons multiplied by 0.2 square root 2 meters. What is that quickly? 0.2 times square root 2 times 98.1 is equal to positive 27.746. Is that what you also have gotten? Yes? Beautiful stuff. Last but not least, I don't think we have time to cover this, but generally we already did this. How do we find this guy? We did it before, right? We used the IC to say that, okay, VG is equal to 1/2, or not 1/2, but my displacement vector from, or 2.g relative to my IC multiplied by omega, and this ended up being VG is equal to 0.4 times omega. I plug this into my formula for VG. Remember that it's squared. I simplify. Long story short, I get my answer, and that's what it is for the most part. I'll give you the final answer since we don't have enough time. And it's very, very simple steps from here. You're going to end up getting that your angular velocity at 0.2 for this rod. Once you plug in all these numbers, you already have all the numbers. Once you get all these lovely guys, you're going to get 6.1 radians per second. And that is your lovely answer, yeah? Beautiful stuff.
Wow.